All right. Video going over equilibrium in a chemical reaction. So let's do that. All right. So equilibrium, right, at its core is the idea that a chemical reaction can go basically both ways. All right. So when you think about a chemical reaction, right, we usually are thinking of a chemical reaction like this. So if I had sodium plus chlorine, right, this is going to give me sodium chloride, right? The implication of the arrow, right, is that these are the reactants. They're going to make a product, right? That's the idea. Chemical reactions, and this is a bit of like a, when I say this, realize it's like it's a technically true, but we would often say some. I'll just say it. Reactions are reversible, okay, meaning reactions can go both ways. There are certain reactions that are so unlikely to go backwards that we basically say they're irreversible. Okay. Um, it's either something that's like the probability is so low we ignore it, or the energy requirements are so high we ignore it, or something along those lines. Okay. And again, I'm kind of simplifying this a little bit, but basically, I want you to think that pretty much any chemical reaction is reversible. Okay, because it's generally true, and the exceptions to that aren't worth not a high school level at the very least, and even at the college level, it's more a question of like why would we say it's irreversible, thermodynamically or mechanically. Okay, but uh, make it simple and say they're reversible. Okay, equilibrium is the idea that a reaction is going in both directions, so going to the reactants to products or going backwards, products to reactants. That's why there's two arrows, right? Equilibrium is when these two are balanced, such as your little seesaw. Okay, equilibrium simply means a reaction is going both ways equally. What does that mean for us observing it? Like if I'm watching the reaction, it means it appears to not be doing anything. It appears to just be stuck, not moving, doing nothing. And you're like, oh, right? Nothing is changing. Okay. That's a chemical reaction at equilibrium. So, if you're looking at, for example, a piece of iron on a bridge, like a strut of iron on a bridge, it doesn't look like anything's happening, right? You're like, nothing's happening. But if you're able to zoom in, you would see the chemical reaction of oxygen hitting iron molecules and rusting them, forming iron oxide. It's a very slow reaction, so it doesn't appear to be doing anything. That reaction, though, is not at equilibrium because it is making rust. The rust itself is not breaking back into iron and oxygen, right? That's not a very favorable reaction, okay? So I don't want you to think that because looking at it, nothing is happening, that necessarily means it's at equilibrium. But you could think of it as, generally speaking, if a chemical reaction is happening, you mix two chemicals together and there's bubbling and fizzing, that's probably a chemical reaction, right? And then eventually it's going to slow down, right, and eventually appear to stop. When it stops, it's technically going back and forth, just at a point where you really can't see a difference. Okay, that is the nature of equilibrium. Okay, this video I'm making for like a freshman level understanding. Okay, it as you can imagine, chemistry can get way more complicated at the college level and the graduate level. So what I'm saying, take it with a grain of salt, but see like it's salt, but it's basically correct. Okay, hopefully it's making sense. So you say, okay, kind of got that, kind of makes sense. This idea of equilibrium. What does it mean for like? What do I need to understand about it? And that's where we have this concept called Le Chatelier's principle. I think I spelled that right. Okay. Again, I'm not a big spelling person. That's not, to me, the reason you're taking chemistry or taking physical science. Okay. Le Chatelier's principle is basically ways in which we can make a chemical reaction go in the direction that we want. Okay. Or understanding why nature is having a chemical reaction go the way it wants, if that makes any sense. Okay. So this is basically how to change the equilibrium conditions, how to change the equilibrium state, how to cause equilibrium to, the word we use is shift. Okay, so if balanced is, hey, it's evenly going both ways, Le Chatelier's principle is saying, how can I make it unbalanced so the reaction has to go the opposite way to what you made it do, if that makes sense? It's like a seesaw. Imagine this is your pivot point. Okay, Le Chatelier's principle says I can make the seesaw unbalanced, and then nature has to fix it by making the reaction go the other way. Okay, and that might be a little bit confusing, a little bit abstract. So let's take a look at what this could look like. Okay, if I had, for example, let's say this chemical reaction. So let's do, we're burning propane probably. Let's do propane C3H8 plus oxygen. Oops, gives us CO2 and water. Okay. This reaction, we first need to understand whether it's endothermic or exothermic. And what that simply means is whether the reaction releases energy or if it takes energy in. Okay? So if I look at this reaction, there's really no way that you could just look at it, especially if you're like in a physical science class, and just say, oh, it's endothermic or oh, it's exothermic. You would need to know about the bond energies. Okay? And for like a freshman level class, what I want you to think about is on one side of a chemical reaction, we're going to have like the total bond energy of one side and then compare it to the total bond energy of the other side. And you say, what is bond energy? Bond energy is simply these molecules we're talking about. So like this oxygen is O2 because get this, it's two oxygen molecules bonded together. Okay, so if you look at this, you're like, that's an O2 molecule. The bond, or in this case bonds, because this is a double bond, have energy stored. And when you say energy stored, you could basically think about this like a battery. Okay, a battery holds on to charge. A battery holds on to potential energy, or is potential energy. In the real world, it's because these two things are together. It would take energy to pull them apart, and when they come together, it releases energy. Okay, but again, this is basic stuff, aka I'm making it basic. Okay, it gets more complex. So this has energy. Okay, the propane molecule is a C3H8. It looks like this. So I have okay, this, let me use my fancy schmancy writing tablets. Makes this a little bit easier because I'm looking at it, I'm like, wow, look, I forgot how bad it is to draw with a mouse. Yeah, anyway. So if I draw this molecule, here's my propane. That's so much better. Here's this propane molecule, C3H8. Okay, again, you don't have to. You do not have to know the molecule, the molecular structure of propane. Okay, but this is what propane would look like, right? 3 carbons, 8 hydrogens. There are bonds, right? There's 1 bond, 2 bond, 3 bond, 4 bond, 5 bond, 6 bond, 7 bond, 8 bond, 9 bond, 10 bonds in this. And you might say, is there a reason I counted it that way? Well, sure, these are CH bonds, carbon-hydrogen bonds. This right here and this right there are CC bonds, carbon-carbon single bonds, and they have different energy. Okay, so, and again, for a physical science class, like an intro to chem type class, you know, I'm not going to get too much into the specifics of the difference, but there is a difference. Okay, and you might be able to kind of intuitively know that a double bond is stronger than, say, a single bond. Okay, and again, it's a bit of a simplification because you could say, what about a carbon-carbon double bond? Is that stronger, right? But for right now, double bonds are stronger than single bonds. Okay, triple bonds are stronger than double bonds, right? So you say, okay, those are the bonds there, and I'm just going to make up a number. I'm going to say there's 1,000 joules of energy on this side. That's the energy stored in those bonds. Say you think about it. And then over here we have a carbon dioxide. That's a C double bonded O. Okay, so that would be carbon dioxide. And then I have my water molecule, which would look like this. Okay, two OH bonds. Okay. It's not easy to just look at this and know which one's going to be higher. Okay, but what I can tell you is we need to take into account how many molecules there are. This is why balancing a chemical reaction is so important. So to balance this, we're going to have 3 carbon dioxides, we're going to have 4 water molecules, and that's going to give us 5 O2 molecules. Okay, and what I'm just going to, again, I'm going to take this for granted, so to speak, that the reactant side is going to have this many joules of energy, and the product side, let's just say, is only going to have 800 joules of energy. Okay? Energy stored in these bonds. All right? And you might say, well, wait, but you just told me double bonds are stronger. It's true. There's 3 of these, right? But I have 5 of these O2 double bonds. And again, this propane has a lot of bonds, right? 10 bonds total. It's a lot of bonds. Okay, a lot of energy stored there. Okay, and maybe you're starting to connect dots, and maybe you're like, is that why we burn propane? Is that like for like a grill, or butane in a lighter, or hexane or octane that's in gasoline? Exactly. It's a very big source of energy. Those bonds have energy in them. Okay. So in any case, you say, hey, 1,000 joules on this side, 800 joules on this side. Because we know that energy can't be created or destroyed, we know there has to be some extra energy that is basically left outside of the bonds. And if you say, how much extra? Well, maybe 200 in this case. Can't destroy energy, can't create energy. If there's 1,000 joules on this side, there would have to be 1,000 on this side. 800 of which, again, this number, I'm making up this number. It's not like it's real. It's way more than 800 joules of energy. Anyway, the point is this. 800 joules on this side, you say there's got to be that extra 200. This extra 200 is released as heat, as light, fire, which is light and heat, right? So this would definitely be exothermic. It's releasing energy. Energy is leaving. It's exiting, okay? Because I only need 800 joules to make these bonds, or rather, when these bonds form, they release 800 joules of energy. Okay, that bond contains that much energy is one way to think about it. So this reaction is exothermic. You're probably saying, how does this come back to Le Chatelier's principle, right? That's what it says right there. How does it come back to it? Equilibrium, right, is that seesaw. And I want you to think, let me draw that again because I kind of drew it a little lopsided, which might, I did it again. Oh my God, let's try. Yeah, that's better, right? The universe wants to get it balanced, okay? I can change the balance, though. If I were to put heat into this reaction, meaning if I crank up the temperature, so this is in a bottle, let's say, if I put that bottle in a hot room, it's going to be hotter. There's going to be more energy. And the universe is going to say, hey, there's energy on this side. There's heat. It's going to say there's too much heat. This balance that used to be like this is now like this. And I got to fix that. How do I fix that? I make the reaction go the other way. And the reaction going the other way would be what? Taking this heat, putting it into bonds, and going this way. Okay? Now you got to realize making propane is, you can't just take CO2 and water and force them together and make propane. This goes back to the original point that what I'm saying about reversibility, like you're not just going to make propane by smushing CO2 and water together. But the idea is that you could push the reaction in the opposite direction. In this case, it would be more the idea that the reaction wouldn't go in that direction anymore. It would no longer make CO2. It would no longer make water. Think of it as the universe says the reaction, or the universe is getting too hot. And the way to reduce the heat is to take that heat and turn it into chemical bonds. Okay? For a freshman level class, for an intro to chemistry type deal, that should be a good understanding of that, okay? On the flip side, if I were to take heat away, if I were to make it cold, think of it as the universe would say it's getting too cold, right? The balance would be like this. And the universe would say, man, it's too cold. There's not enough energy. I better move the reaction in the direction that is going to raise the heat. And which direction raises heat? Well, it'd be going that way. If I go this way, it reduces heat, which means it's exothermic going left to right, endothermic going right to left. Okay, that's the core idea here, all right? And if that's a bit confusing, if you're like, I'm still kind of not sure about it, you got to picture it as every chemical reaction is either endothermic or it's exothermic. And if I flip the reaction, it means now it's the opposite, right? If it's endothermic going this way, it's exothermic going that way. And Le Chatelier's principle is, how do I change the balance to make one side or the other favorable, okay? It's an abstract idea. It's not easy, but I'm hoping it kind of makes sense. All right. So that would be for heat. All right. And I'll make another video talking about pressure, which I think is a little bit easier to understand. Okay. So if heat is kind of confusing, pressure should hopefully be a little bit easier. Okay. But it's very important you understand the heat part too. Okay. Le Chatelier's principle is about several different ways to change the conditions of equilibrium. All right. Well, we'll call it quits there. Have a great rest of your day.